Khalid. I'm part of the first phase, I guess, and I'll be presenting our lecture on binary search. Before we go through this, this is a fun question. Anyone had a dictionary, a physical one, during their childhood? Raise their hands. Okay, I'm going to ask anyone, but can you tell me how you actually search a word just randomly? Anyone?
Well, you just
just
guess where the letter is.
How would you go about searching? If you had a word like hat, how would you search?
You just I think you go from the half page.
Okay.
And then you go back if you're after H.
Yes.
And if you're before H, you just go from.
Then afterwards, after you find H.
And then you again after you find H.
Yeah.
The next letter.
A, right?
Yeah.
Basically, that's what binary search is. You just have to find it by minimizing your search space every single time. So if you had, let's say, a list of sorted elements between 1 up to 6, what you would do normally, it would be linearly searching, right? In binary search, what you do is you keep minimizing the search space. And for that, the algorithm is every single time you have to pick the middle. And with that information, you have to go through a set of checklists where if the element is below the list, then you have to check the right side. And if it's greater than the element we have at the middle, then we'll check the left element. And if we find the element, then we'll actually return the list, I guess. So if you had from 1 up to 6, and we're supposed to search for 5, first you divide it into 2. Then the middle element would be, I think in this case it would be 3, because 0 plus 6, yeah, it would be 4. So since we're technically finding 5, we will compare it with 4. Since 4 is less than 5, then we're guaranteed that the element will be in this half. If we are supposed to search for 2, then we'll be guaranteed that it will be in the left half. So we will completely discard this, and search within this search space, because 4 is not equal to 5. Then we'll check for the middle element of this one, which is 5, I think, since 0 plus, yeah, and this one I think it's 6. Since 6 is greater than 5, then we'll check the left side. Since 5 is equals to 5, then we'll guarantee that we had found the element we were searching for. This is basically what binary search is, completely minimizing our search space at every turn till we find the element, and if we don't find it, then we'll keep searching for in the left and right half, and if we are completely clueless about it, then we'll return -1 because we haven't found the element. So yeah, let me go back and recap all of it. Linear search, which is the brute force way, is given a sorted list of n elements. We are supposed to find an element E in the array. So the naive solution would be iterating over each element till we find the element we are looking for. And this in time complexity would be of n, because at worst case the element would be at the last element, at the last index, and this will be our worst case, which is of n, n being the length of the list. Does that make sense? So binary search. Okay, let's go over the pseudocode or basic algorithm for it. So if you're given a sorted array of elements, and I mean sorted in the technical term, because if you're given an unsorted array of elements in which every element is jumbled up, you cannot implement binary search because the algorithm would not guarantee us that it is on either end. So if you're given a sorted array of n elements, you're supposed to find an element that you're given, and what you do is every single time you check for the middle element. When you find the middle element, you check if it's directly correlating with the element we are searching for, which is target. So I'll use target instead. So you check the middle element with the target. If it's equal, then you return true. If it's greater than the element, so in this case, if we're searching for 5 and the element we find at the middle is 4, then we are guaranteed that the element we are finding, which is a target, will be to the right of every element next to the middle. Because if it's continuing like 7, 8, and 9, 5 would not be within the left side. It will be guaranteed that it will be on the right side. And if we are supposed to find like 2, 2 will not be on the right side. It will always be to the left of the middle element that we're searching for. This is binary search. So we keep doing this until we run out of space. So if you end up with a search space with this element, with one element only, and if we don't find it, there's no way we can go. At this point, we'll return -1 or we'll return false, depending on the question you're asked. This is the algorithm of binary search. Anyone have any questions? All clear? So yeah, let's go over an example. So if you're given a list of numbers from 2 up to 91, and you're supposed to find 23, what you do is first, you check the middle element, which in this case is 16. 16 is less than 23. So we are guaranteed that 23 will be on the right side of the middle element we are currently at. So we'll check the numbers from 23 up to 91. And we'll check for the middle element between those ranges. And the element at the middle between those ranges is 56. But 56 we find is greater than 23. So we are guaranteed that it will be between 56 and our previous element pivot, which is 16, right? Because we already have traversed from 16 up to 2. And we're guaranteed that the element will not be in between these ranges. So we'll search between 23 and 38, which is our current search space. So we'll take the middle element. At this stage, the middle element is the element itself, 23. At this stage, we return the index. If the element we are searching for was 22, because our search space does not include it, we'll return -1. Does that make any sense? Everyone clear? Also, let me know if I'm going a bit too fast. Okay. Okay, this is some sort of animation which compares binary search with sequential search. What you're supposed to find is the element 37, but for sequential search, since you're going one by one, you'll only reach it by iterating until 11 steps. But using binary search, you can do it in like 4 or 5 steps. Actually, like 4 steps. So I have a question now. Like, compared to linear search, can you fill this out? Like the average cases, the base cases, and the worst case. Actually, for average cases, it's general. What would be the average case time complexity for binary search? Anyone? Should I pick randomly? Maybe I should. Yeah. Sorry. For average case. Okay. And it's because? Since we're actually like minimizing our search space by half at each time, this will lead us to a time complexity of log n. As for the base case scenario in comparison to linear search, anyone has a guess? Like, at what time would be the best case to use binary search compared to linear search? At which position would the element be positioned at?
It's right in the middle.
Exactly. If the element would be was found at the middle, like in this case, I think it's 23. If it's at 23 exactly, binary search would find it at 1 step, compared to sequential search, which would take, I think, off and over 2. That much step. And the worst case would be compared to sequential search.
When all the elements have been or you can say
Which position?
Not in that case.
In this case.
I guess 11.
Is it though? Why?
because all of the items have been discovered. What do you call it?
Makes sense, but the absolute worst case, like with this example, choose a number from this, in which binary search will perform at the worst case compared to sequential search. One, exactly. You're right. Who answered it? Thanks. Yeah. If it's at the first position, sequential search will find it like completely immediately at the first stage, whereas binary search would have to iterate till it finds it. That's the average based in worst case. Make sense?
What about 59?
59 would be actually a good case for binary search, because it would, like, every single time it would go half to half. So in this case 23, then 41, then 47, then 59.
Yeah, just like what?
Yeah, but sequential search would go like
Oh, okay.
complete. Yeah. So in comparison to sequential search, one would be the worst absolute. Okay, if it's clear, I can go over the implementation. It's clear, right? Okay, for the binary search can be implemented in both recursive way and iterative way. What you do is, for the recursive case, all you have to do is check if the right pointer we're holding is greater than or equals to the left pointer, meaning if we haven't crossed each other. So in this case, if you are holding left at the first element and right at this element, as long as left and right are in between each other, then the recursive case will hold. But once right overpasses the left, then we're guaranteed that we have exhausted every single possibility. So for the implementation, all we have to do is check for the mid element. Then if the middle element is equals to the target, then we return it. If the middle element is greater than the target we're finding, meaning if the target we're finding is 2 and the middle element we find is 4, then we'll modify our right pointer to be within this range. So the right pointer will move to this position and we'll search within this bounds. So what we do is, the left would be the element, the left will not change, but the right pointer would be one element behind the middle element. And for the right case, it would be almost similar, but they're changing the left pointer instead. Make any sense? Good. So yeah, this is how we implement it recursively. Any idea on how to implement it iteratively? Just brainstorming. Yes.
Just like this, while the right is greater than left, we keep on updating the mids and performing the actions, the boundaries.
Yeah.
When the right becomes greater, we know we have eventually run out of space. So
Exactly. What you have to do is use a while loop and just keep on modifying the left pointer and the right pointer. This will be the iterative way. Basically the same idea, just doing it in a while loop. Okay, this is a fun teaser. Okay, given this binary search implementation, can you come up with a test case where this code might actually break? I'm going to give you guys a couple of minutes. Also, as a hint, don't think from a Python perspective. Yeah, it doesn't matter, because the array links, if it's empty, then it will be 0 less than -1. The loop would not work. It will run on it if it's an empty.
Maybe the mid is integer and this buffer, right? May give us something.
Exactly. But I'm not sure. Are you thinking about the float one? If it's the float comparison to integer? Yeah, that actually is correct, but it will still not break it. Like the code will still run. I'm expecting the code to actually completely fail. Maybe in the crash your PC.
What if left is equal to right? That was out.
Still.
What if you have left plus right is the sum is odd, and when you divide it by 2, that
Still
will be
converts.
new. We are accessing array by that index, so array up to 25 will be, for example,
Yeah, but integer will still convert it automatically. If it's 2.5, it will convert it back to 2.
it's not by 2.
Yeah, it's not Python. I think it's Java. Java or JavaScript.
I don't know, I'm not sure. What if the target is very big? Does this keep running?
If the target is big,
Yeah. Maybe bigger than infinite group.
yeah, but it will still break. I think the integer is like, I don't know, 1,000,000 or 1,000,000,000. It will still like compare it within the array. Right?
The right variable is zero.
Yeah.
The return value of I is very big. And X is very big in the
Exactly. You got it. Like if you are given an array of like 2 to the integer max, if it's like 2 raised to 31, would this code actually work? Like if the, for example, if the left one is like at the middle, which is 2 raised to 31 over 2, and the right pointer we have is 2 raised to 31, would this code work? Wouldn't it overflow? It would be like, this code would actually break because it would overpass the limit of integers. There's there's actually a code that was not actually found in Java codes for like 9 years, and it was a bad implementation, I guess. But it has a history like, for 20 years. And also a bonus question, is it realistic in real-world systems to have a memory size of 2 raised to 31? In Google or like big companies, it might work, but in real world, like in our normal PCs, it would fail because 2 raised to 31 would have around 8 gigabytes of memory size, and that would definitely break our system. And yeah, what we do is use left plus right minus we use this one instead because this will guarantee us that the implementation we have will work. Also, I think we have an example for it. I'll go over it if need be. But yeah, using the traditional approach, if our left element is 2 raised to 31 over 2, and our right index would be 2 raised to 31, this would definitely overflow because it will overpass our integer limit. And if you try this approach, it will definitely guarantee us that the same approach we have here would work, and it will still be within the range of integers. And also for Java, I think we can use long, but we cannot access using long elements. We have to convert it back into int, and that would still that would work, but at the same time, it has its own complexities. Okay. There's another one. The same question, but could there be another bug as a bonus? This is not as the previous one, as a bug, but Yeah, the previous one it's a kind of a memory issue, but this one is a bug. Like you can fix it and it will not break your system. Think of it as a programmer problem.
If there is only one element in the array and if that target is that number, but since left and right will be equal, it will just return negative.
Thank you. Anyway, let's run over it for an example. If you're given an array of from 1 up to 7, 5, 6, 7, and first at our left would be here, right? And our left would be 0, 1, yeah, 7, and our right would be 6. Then at one pass, it would be 0 plus 6 over 2, or using that formula. So 0, 1, 2, 3, our middle would be here. And at first pass, it's all good. Like if you're, yeah, the target would be, I think, let's say 1. So at first pass, we get to the middle. Then we'll run over our, our code, and our right would be mid minus 1, since the target is less than the middle one. So we'll check through this one. So our right would be here, which is 2. Left is equals to 0. And this one would result in the middle being here. And still 2 is greater than the target 1. So our search index would be here. And our right would be 1 minus 0, which is 0. But our code will not run because left is still greater than right. And 0 is not less than 0, so we'll miss the element we're looking for. Make any sense? You still could use this approach, but at the same time,
Left is on 0, right?
yeah, right is still 0, because we are moving 1, right? Left 0, right 0.
Yeah.
But our code is not right.
Wouldn't then it be 0?
Yeah, but we'll still go over the condition, right? While left will be right.
I think it's right. I mean, just the last case condition finding that.
Not really, because we were at 1, right? Our mid was 2, and our mid point was 1. So once we check this one, 2 is greater than the target. So right would be 1 minus 1, 0. Then we go over to the conditional case. Left is still greater than right. 0 is not less than 0, so we return minus 1. This could be this. But depending on like the question or the implementation choice you have, you can actually implement it using left less than right, but you'd have to modify these two variables. So using this left less than or equals to right, to check for every element, what you do is move the left and the right every single time by 1. But if you want to actually use this approach, all you have to do is move one of them, either the left or the right. One of them would stay at the middle element. So if you're using left less than right, you can either leave left is equals to mid and right is equals to mid minus 1, or you can use left is equals to mid plus 1, or right is equals to mid. Depending on your implementation approach, you can find a way that works for you.
The first idea would be just finding the next closest element than 8, which is 7 right now.
Okay.
We will use binary search for that.
Okay.
For example, let's say mid is the 7, the second 7. If it is less than 8, there might have another element that's closest to 8. Then we have to just update our mids to the right side, so that we will close to the element
As possible.
as possible. Same for the next greater one.
Which is the target plus 1.
Yeah, but it might differ. Like we don't know, maybe it might be there might have maybe 20, for example. In the first search, we can say, let's say we found the 7. We can check if there is an 8 or not. If there is no 8, since we know this is the, we can guarantee that if there is no 8, we can guarantee we can just return -1. Then we just if not, we can run the second time binary search.
Okay.
Yeah.
When you get to 7, are you going to go one by one till you reach the
No.
last element?
No.
Okay.
In each step, we are using binary search again. And vice versa, we can also do binary search for finding the 8. I mean the 8 like right side and left side.
Yeah.
Same approach, just for the this time target, not for the less and greater ones.
Yeah.
I think
Just have to like find the starting point and the ending point.
any point of the target, yeah.
So in total, how many binary searches?
2 times. Actually, we are running 2 times binary search. I think it's gonna be
So in total, time
2
complexity.
again.
Half and
Yeah.
log n.
Okay.
Any ideas?
We just know the size, the length of RHA. We bisect it and we find the same size. So until we find the first element. I mean, if we got it, if we are sure if we got it, we will stop the binary search. Once we find it, and after we find the element, we will do 2 binary searches.
Okay.
That's because if we find 3, there may be 3s before it and we need 3s before it.
Yeah.
So we will do the message to this side. And if we are still on 3, we will trust the sense and the middle element, the last element. By this way I said, we will see.
So in total, around 3 binary searches, like 1 for the checking the existence.
The binary search size will be low, but the size of each binary search is going to be smaller. And at our worst case, this would be bigger.
And the time complexity will be?
3 will be.
Any other ideas?
This is not better idea. This was the first approach. So we just run 1 time BFS to find if there is 8 or not. If there is 8, we can just linear search to find the right
That's the
side.
worst.
Yeah, it's gonna be
Also, I wanted to ask, would it be feasible, wouldn't it be like easier to actually find the target instead of the numbers we looked on the greater one?
7 might not exist too.
Yeah. Any other ideas?
I don't even know if it will work. But we're gonna do binary search. But when we do our find value, when we return the index, if we get the previous element is less than the target, and ourself is equal to the target, we'll do that first, and then we'll do the same thing for the other side with binary searches.
Kind of like the first, no, the second solution for it. Not the this idiotic one, for the linear search one. That will take a longer time, no offense.
Yeah.
Yeah, if it's all 8s, that will take like often.
Actually, it depends on the number of 8s, but yeah, most probably there are gonna be 8s.
Exactly. But the other one with finding the target and going the other way, kind of like that idea. Any other solutions? But yeah, that's the most efficient one. You just have to, when you implement it, it will be a bit tricky in that you have to continually check if it's if you're searching for the left one or the right one. Like for the first one, you just have to keep modifying the right end till we find the end, and for the right side, you just have to keep modifying the left one. So the brute force complexity would be checking every single element till we find the first and last in this. And for the efficient one, this is actually a longer code, a really long code, but what you do is kind of like your idea. For the first one, you just have to find the starting and the ending element. For the start, when you find the target, if you're searching for the first index, just have to keep modifying the right operation till you accomplish or find the first index. And for the searching the right index, you start from the start up to the end. And that will guarantee us that what the element we find is within the bounds. Make any sense? Any questions? Okay. Okay. We're about to finish, but this is a bonus one. How do you insert to a binary search tree? Like, if you're given a sorted array of integers, create a binary search tree. Like, imagine how you'd build it using these numbers. Ideas. You can even repeat those. Doesn't matter. But yeah, given these numbers, you can even you can iterate from the start to the finish, meaning 1 being the root node, and followed by 2, then 3, then 4, then 5, then 6, then 7. Or you can start from the end, which is 7, and go to the left side. You can randomize it if you want. You could also like jumble it like 1, then 7, then 2, then 6. It doesn't matter how you do it. You could also pick the middle always. This is how binary search trees are made. Iteratively, you can go like this, you can go randomly, or the most efficient way to create a binary search tree would be picking the middle. Then, within that subset, you then pick the middle, and you keep inserting every single node. This is how you create an efficient binary search tree. Actually, I was asked this. You asking me this like in the first place? Yeah, this is how you implement a binary search tree. Any questions? Yeah. Okay, that wraps it up. We have added a few questions to the sheet, around 9 questions. We also like plan on categorizing it. If it's possible, you have to do the first 3 questions. Those will guarantee you have at least a few, at least a tiny bit experience with binary search, and we suggest that you do the rest of the questions to gain a further understanding. But the first 3 questions, kind of a must, okay? Everyone do it. And we'll finish up with the quote of the day, I guess. This is by a soldier called Archilokos. I'm not sure if I'm pronouncing it correctly. But the quote is, "We don't rise to the level of our expectations, we fall to the level of training." So it all depends on how much committed you are and how persistent and how dedicated you are to your own progress. And at the end of the day, it always ends up to that.